Hello, everyone. It's my pleasure to present topic Knowledge Graphs Introduction. The presentation will be delivered by Todor Primov and myself, and this is a very introductory presentation for the knowledge graphs. First, we'll start with the discussion, what is a knowledge graph. Later, I will discuss briefly how do we represent information in knowledge graphs. I will briefly discuss the topic of ontologies, taxonomies, etc. And Todor will present more complex entity relations presentations, and we'll discuss briefly how can we use knowledge graphs for different applications. At the end of the session of the presentation, we'll have a question answering session, and please feel free to ask your questions. What is a knowledge graph? Actually, we're using knowledge graphs on daily basis because when we're searching on different, using different search engines or using, for instance, Wikipedia or other resources, behind them actually are used different type of knowledge graphs. For instance, when we see the Wikipedia page, here we see a raw text, unstructured text describing the concept. And also we see at the right-hand side a panel describing in more semi-structured format information related to breast cancer. This information actually is stored in a knowledge graph, and we can see also different resources available on the web, which represents different types of knowledge information. The widely used resource alongside with Wikipedia is Wikidata, which is considered as encyclopedic open data knowledge graph. And we can see in this very well organized information about different concepts which we are going to use in our project. For instance, let's here type breast cancer and see what kind of information we can find in Wikidata. For breast cancer, we see that here is available information about the concept labels for various languages, for English, also for our targeted languages in the project. We can see also, for instance, for German, for Dutch, also for Estonian, and for many, many other languages. We have also here structured information, not only about the concept translations for different languages, but also for the organization of the information of this concept regarding different types of standard classifications which are used in medicine. Here you can see International Classification of Diseases, 10th revision codes. Also, we can see also relation to UMLS here, the concept which is corresponding to this concept. A lot of relations with genetic associations, also with drug therapy used, medications, risk factors, etc. This one actually helps us to use this well-organized data in linked open data like Wikidata and other public resources to do different type of inferences, and also to extend our data with such information, which is the domain information, and which allows us also to benefit from different external resources. I will now present the Wikidata information using the MetaFacts studio. MetaFacts are our company partner, and we are using this MetaFactory tool to present different knowledge graphs visually. When we use MetaFactory, we can explore the data from Wikidata in more user-friendly visual way. Now let's explore the concepts which are presented in Wikidata using this tool. I will go back to the live demo. Here for breast cancer, we have structured information for all of the concepts and relations which are available in our huge knowledge graph Wikidata. For instance, let's see what kind of information do we have for risk factors recorded in Wikidata. We have mentioned only one risk factor, which is smoking. This doesn't mean that these are all risk factors. This is the current information in Wikidata, which can be extended with additional information. Here we see two concepts, breast cancer and smoking. They are called also concepts, entities, nodes. Sometimes they are called also subjects, objects. We use different names for these concepts in knowledge graphs. And we have here one relation. It's also called link, sometimes property in this very small knowledge graph, which contains only two nodes, one concept breast cancer and the other concept is smoking, and we have a relation between them which defines the ground truth statement effect that breast cancer has risk factor smoking. This very small knowledge graph can be extended with several other links. I will add here some additional information that we have from Wikipedia to see more complicated view of knowledge graph. Let's now see some gene associations. We see that there are too many genes. I will just show one relation. I'll select this one. And now here we see that we have two concepts, breast cancer and CHST9. This is a gene. And we see here two relations. These relations are actually relations which are directed. We have one relation between gene and disease and another relation which is between the disease and gene, which are gene is associated with the disease and the disease is associated with the gene. It's not the same with smoking and breast cancer. Breast cancer has risk factor smoking, but smoking has no risk factors. This is not symmetric breast cancer. And we can also extend more this presentation with more complicated relations. Also, we can expand here relations for drug and therapy used for also relations for risk factors because smoking is not only for breast cancer risk factor, but for many other diseases. And we see here that smoking is a risk factor also for myocardial infarction, for many pulmonary diseases, Crohn's disease, etc. And we can have also more high-level organization of the concepts because breast cancer is a type of breast disease and also has a subclass of breast neoplasm. And we can also explore the anatomical location of breast cancer, which is the anatomical organ breast. And for knowledge graphs, we have concepts which usually we present with different geometrical shapes when we're visualizing the knowledge graphs. In this particular example, we're using here circles, but for previous examples, the concepts were presented by rectangular shapes. Also, we call these concepts nodes, entities, objects, subjects. They describe each other in the knowledge graph and provide actually the basic concepts information. And we use also relations or connections, which are represented by arrows, which represents the context in which these concepts are related. In this example, we have medication and disease, gene, proteins, and we have here that diseases and genes have genetic associations. Medications are used for therapy and treatment of certain diseases, and they are used for certain medical condition treatment. For knowledge graphs, we have different presentations and different use. They can be considered as a database and can be cured, or they can be considered as a graph and can be analyzed as a network, or they can be used as a knowledge base and new facts can be inferred using different techniques. How do you represent information in knowledge graphs? Represent information in knowledge graphs, there are different techniques, but the most widely used is the RDF, Resource Description Framework. This is a graph data model. This is a standard by W3C, and it formally describes the semantics or meanings of information and represents metadata, data about the data, and represents the relations, links, or edges in the RDF graph. And the basic form of presentation of information is triple. RDF triples contain subject, predicate, object. Let's come back to the example with breast cancer and risk factor smoking. We can consider this as a triple in our graph where the breast cancer, the first object is called subject. The predicate or the relation is risk factor in our case, and the object of this relation is smoking. We can read this one like breast cancer has risk factor smoking, but the opposite, the symmetric one, smoking has risk factor breast cancer, is not true. Here, for these triples, because this textual information is not unique, there are different ways to present the concept names, the relations names. We're using so-called universal resource identifiers, which presents unique disambiguated concepts presentation. As in our example for Wikidata, we have Wikidata unique universal resource identifiers, URIs, which are presented with the form. Here I'm presenting them with the form which is Wikidata. This is a prefix, and the concept actually identifier, which starts with Q. Let's go back to the Wikidata and see here we have this Q128581, which is the unique identifier for this concept in this knowledge graph Wikidata, in this knowledge base. Again, for smoking, we have unique identifier, which is Q662860 for this knowledge base, which is Wikidata, this one. And for the relation risk factor, the relation identifiers in Wikidata starts with P, the capital letter P followed by some digits for risk factor, the unique identifier for this property, for this relation. The identifiers actually, universal resource identifiers, actually refers to the following URLs, which we can use to access the concept description. Here it's Wikidata entity and the corresponding ID, and for the property and the corresponding ID. For our triple, this is an ordered triple, starts with subject followed by predicate and object, and it's represented in our case by 3 URIs. This is a general method to describe data and the relations between them. And this RDF representation is built around existing web standards like XML and URL. And we have 2 types of information that we can present. Some information can correspond to existing universal resource identifiers, but some information can be presented like a free text, for instance, some strings, textual descriptions. Also, we can use numerical values, dates, etc. Properties represents relations. They're always represented like URIs. And the subjects are also always representing URIs. They are always concepts represented in our knowledge base. And the objects can be either resources or literals. And we have also some ways to resolve those literals using XML schema for data types. For instance, here we can see for some language tags used, or schema for data types, or specific types for pieces of text. These triples are the fundamental presentation for knowledge graphs, and always we have resources, unified resource identifiers for subjects, also URIs for predicates or relations for properties, and we have some flexibility for objects, either URI or blank node or a literal. URIs allows us to have connections between different concepts in our knowledge graph. Here we can see URIs presented like blue ellipses, and the literals are presented with pink rectangular shapes. The literals are human readable, but because we have a lot of freedom to present the information there, they actually don't provide too much to the connectivity in our graph. The syntax is used to store the information in RDF. Usually include the XML RDF presentation. Here we see an example for presenting information for helium. And this is the concept helium. And we have atomic number, which is 2, atomic mass, which is 4.002, and gravity, specific gravity, 1.6 E minus 4. They're used also different formats like turtle, which is more compressed, but still human readable. And here we see the same information presented in turtle format with the different types of relations, atomic number, atomic mass, specific gravity. And here we see these numerical values actually are literals, and the helium is our URI with the relations to those literals. Widely used format is JSON. For JSON, here we see a compressed version of the values, and for the same example for helium, we see presentation of the different relations and the corresponding values. Let's now go to an example on Wiki. Wikidata provides a query service, which is a service that allows us to search for different data and different relations between them. This actually is formal query language, which is quite similar to SQL, which usually we use for relational databases, but with some extensions and slight differences, which allows us to explore such databases, which are NoSQL databases. In this example, we're searching for diseases, and this is actually searching for URIs. In our case, here we'll see the result for URIs for diseases in Wikidata and disease labels. We already saw that for breast cancer example, which we used as an example for presenting information in Wikidata, we have labels on different languages. Those labels are textual information, they are literals, and here disease label will represent the literal corresponding to this URI, which is in our case breast cancer. For this URI, I'm using just the English language for the label, and I'm looking for all the drugs and drug labels which are used to treat this particular disease, which is represented in disease ontology with this concept 1612, which corresponds in our case for disease ontology for, let's go back here to the disease ontology, to the concept breast cancer. Here is the concept, which is with identifier 1612 corresponding to breast cancer. This is the disease ontology, and this is the ID in the disease ontology related to breast cancer. I'm looking for the breast cancer and also for drugs or therapies used for treatment of breast cancer. When we run this query, the query actually identifies all the drugs, their URIs and their labels in English presented here. We can also download this information in JSON, in tab separated format, or in tabular format, or we can also represent this information visually like a graph. And let's now see how it looks like a graph. Here is our core concept, the breast cancer, with all its description information related to medical examinations, classes, subclasses, and all these white ellipses corresponds to different drugs used for breast cancer treatment, which are recorded in our knowledge graph. We can also go and explore all these drugs and information for them. Also, we can see the JSON format of this information. This is downloaded automatically from the query service. And here you see the risk factor value. This is the literal type, and the property, which is risk factor corresponding to this type of relation. And this is a relation between our breast cancer and different types of diseases. Here we see also the literal, which is human readable version of all of the diseases for which we have information that smoking is a risk factor. Also, we can explore more complicated queries for drugs and diseases interactions on cancer. This is a more complicated query, which shows us all interactions of cancer diseases and all the drugs used for their therapy, and we can expand and explore information for all these diseases. We can just click on one of them. Oh, I first need to stabilize this one, and then to go further and to explore. Unfortunately, it's quite dynamic. Here is our breast cancer. I can see it, but the graph is really dynamic. And we can explore for some particular disease the relations. I provide also links to these queries, and you can explore later. And let's go to the ontologies, which actually allows us to use domain-specific information on the top of the particular information for some concepts. We have taxonomies, vocabularies, thesauri, topic maps, logical models, and ontologies on the top, which contains a lot of valuable information for the domain, which can actually allow us to make a different type of reasoning and to have some type of generalization of our inferences. We have partonomy. Partonomy is a classification based on parts relations. We are all aware about different chemical compounds, and usually this is widely used as an example for partonomy. And taxonomy is a classification based on similarities of objects. Here we see a taxonomy of different species, biological species, and families, classes. Here we have a hierarchy of concepts, and the only relation between the concepts is parent-child or subclass, superclass, or broader and narrower. And the most advanced version of concepts organization is an ontology, where concepts and properties in the domain are presented in different various types of relationships. For instance, in case we have a hospital, which is one concept, and we have a person, which is another concept. Person, from one point of view, can be considered as a subclass of mammal or biological object. From the other perspective, a person can be considered as a social individual, and this individual have, for instance, a social role, has different type of position in this hospital or relation to this hospital. For instance, this person can be a patient, or can be an employer of the hospital, can be a doctor, also can have different type of roles, to be spouse, or to be married to some other person, or to work for this hospital. And the hospital also can have different relations describing this concept. The ontologies were widely used, and they're inspired from biomedical domain. We can see in BioPortal, which is another useful resource, a collection of more than 1,000 ontologies related to biomedical domain. And we have also a mappings between these ontologies. Here we can see a view of SNOMED with the concepts and the relations like classes, subclasses. In this visualization, also we can select specific concepts and see the mappings between different classifications and ontologies provided by BioPortal. Why do we need ontologies? They provide a common understanding of information, explicit domain assumption, supports data integration for analytics and apply domain knowledge to data, and support interoperation of applications, enable model-driven applications, and reduce time and costs of application development, and improve data quality and metadata and provenance. Now I'll give the floor to my colleague Todor to continue with more examples.
Thank you, Svetla. Okay, so RDF schema provides the meaning of, defines the classes and the different type of properties that are relevant between each pair of classes, or data properties that describe a specific class of entities. Also, it covers the hierarchies of classes and properties, and for each of those properties, it determines the valid domain and range. In other words, for each of those properties which are allowed to be used, subject and object for that property, because you can define certain constraints on, let's say, for example, for the type of a relation encodes, you can define a domain to be a gene, while the range to be a protein. So specifying that gene can encode a protein, but no other type of relations between other classes are allowed. I will not go in very details how exactly the RDF schema differs from XML's schema, but one is, yeah, more or less focused on the open world assumption versus closed world assumptions. And just to mention that RDFS or the RDF schema is not supposed to be used for validation of the data in RDF, while we have other approaches and standards already established working on top of RDF knowledge graphs that can be used, like Shackle and Shakes, which are exactly defined for that particular purpose. Part of the RDF schema and other ontologies that you can define on top of RDF data are the entailment rules and axioms that actually are used to use the instance data combined with the schema of the data to infer new type of objects and relations between them. This is also used in terms of, for example, post-coordination rules definition in some of the ontologies, or inferencing of other type of facts that we can think of. I hope that the next couple of slides will be not too technical, but I think that they're quite relevant for our project, because we'll focus on how we can model more complex type of relations and relations. In our case, this is relevant for modeling of time series, different events on different time, or also modeling of the provenance of the data, because one and the same facts can occur from different sources, and we need to model this information to be available in the graph in order to be used subsequently in different steps. Really, the most standard and widely used mechanism for modeling such NRE relationships is the standard reification. Imagine we have a statement that a certain person has a position, and the actual position, like Abraham Lincoln, has the position President of the United States. So this is expressed as this RDF. Schematically, we have a node object, which is the object for the person. Then we have another node in the graph, which is the actual position, a concept from, let's say, a taxonomy of all the different roles or jobs. And then we have a relation between the two instances of those two different classes, which specifies the semantics. However, then we need also to have an additional object, which will model or will contain the information about other properties which are relevant to be captured in this particular case. Is the duration of the period actually when the person started this particular job. And then we actually define a new object for which there is a relation to, as an RDF subject, to the actual subject. Then we specify also what is the predicate, and then the object, and then we attach as many additional properties as we need based on the how we are planning to use the data, whether it could be start and date, or it could be, for example, source of information, who state this particular statement. It could be official source from the White House, or it could be, for example, a newspaper or something else. So we can, in this way, model the data. So it has both pros and cons in this case. It's very aligned with the RDF data model specification. It's really quite simple and can be supported by all different triple stores. However, combined with huge amount of volume of data, it could be quite expensive and slow to query such knowledge graph and to subset specific facts that satisfy your particular needs. The other approach is really to have a special new object that you define to model this particular type of information. We introduce a new object, job position and one, which is of class position held, and then we model as different properties the different attributes which are important for this particular category of information, like the person, position held, and the start and date, and so on. It's again supported by all different RDF triple stores, then slightly increase the complexity on the ontology level, and it's sometimes different to traverse the graph to find different chains of different facts which are related to each other. And also it's very difficult to maintain the evolution of the database, the schema knowledge graph. Another approach is to introduce a singleton property. You can see that we can have as many predicates as we need in order to express the different positions or timeline events that we might need to capture to cover our use case. This is not okay when you would like to infer new facts based on such a type of relations, because it will be difficult to model them in the ontology and then to apply those rules, axioms to work on top of those properties. And it's also quite inefficient because the indices that needs to be built on top will be much larger compared to other approaches, and also have another technical complexity in defining the mechanism for maintenance of the different identifiers on the properties. This is very widely used approach when you don't have, for example, too many proven sources, and then you actually don't work with actual triples, but you work with actually with quadruples. All the triples are imported in specific context, which is the fourth element of the element of the knowledge graph. And these name graph contexts are, let's assume that we would like to model a case for provenance. Each name graph will represent different provenance source. However, as I said, it's optimal when you don't have too many provenance sources, and then you can model it. Otherwise, again, the index will become too big, and the querying and the filtering of the different provenance sources based on name graph will become really very slow. Okay, the next one, it's introduction of a complex object, in which in most of the cases represented like by a blank node, and then like with the additional concept object that was a previous example, you model the different properties attached to this context object. It's also a mechanism that will increase the complexity of all queries, and cannot be used when you actually would like to apply inferencing rules on top of the this particular knowledge graph and this property. And finally, this is still a standard which is not yet approved. It's a draft, RDF star. Here we have our fact model as a triple, like Abraham Lincoln, the position held, and President of US. And then in another triple, we have a subject, the first triple, this complex object here with the double arrows, opening and closing arrows, enclose another object. And for this object, we attach all the necessary attributes that will model the in this case, for example, the temporality, but it could be also provenience and so on. This is with analogy to the property graphs. This is attaching a properties to the edge of the relation. This is a similar functionality or capability of the RDF-based triple stores. And really, it's quite elegant way how you can model much more complex n-ary relations. And it's very efficient in terms of querying, also in terms of query syntax. It's quite simple. It doesn't introduce any problems with the schema evolution. And the only drawback is that actually not all of the currently available RDF triple stores support this standard, because it's actually not all fully approved standard. It's a draft version, but soon will become. So the good news is that GraphDB already supported it since 9.2. Currently, we are with version 10, so it's quite efficient, tested, and it could be used. In other words, we have 6 different mechanisms that we can choose based on the specific of the use case, how we can model really very complex data.